Jesus. Okay. So what we did last time was talk about the mean, the median, and the mode. The mean is what they call the arithmetic average. You add them all up. And then I talked to you about some principles of the mean, which sound like gobbledygook. But I'm sure you wrote them down because somehow they're important. But now I want to talk about these frequency graphs as they relate to the mean, the median, and the mode. So once again, a normal curve. Wait, you know what? Hold on. I'm going to stretch everything out big so that I can fit a lot on one page here. So, and it'll look better like that. Yeah. Okay, so we have a normal curve. These are the scores for something down here. Low scores to high scores. Over here, hold on. Over here, we have frequency. Starting at 0 people and going all the way up to some huge number of people, some big number. Okay, a normal curve, the mode's the high point, the median is the middle point, which works here because this is a symmetrical bell-shaped curve. And as it happens, when you add them, why does it keep doing this? When you add up all the numbers and divide by however many there are, the mean is the exact same number. So the mean, the median, and the mode are all at the high point in a normal distribution. Whatever this score is that's down below is the mean, the median, and the mode. Whatever that score is right there. And it's going to be the center score in the distribution. Symmetrical and bell-shaped, that helps us know where everything is. There are lots of things that come out like a normal curve. In fact, the data you collected, surprisingly, because a small group like what we got usually is off a little, but your stuff was pretty much a normal curve. All right. I'm getting distracted because some people are talking to other people in the room and it's hard not to watch. It doesn't always go like that. Sometimes we end up with a curve like this one. That's too tall. This one where, so we still have frequency. And these are scores, low scores, high scores. So we have sometimes got a situation, think about a really hard exam where more of the scores are low and a few are still really high because those people always are scoring high no matter what. So you get like, it tends to look like this or something like that. Do you see the whole, that whole graph, or do you see the grid of people in front of it? Like, do I need to move it like that? Doesn't, or if I do this, or is there something in front of it? Can you still see it, or is it blocked by a grid of faces?
We can move the grid of faces out of the way, so it's fine.
All right, so you're fine wherever it is. Gotcha. All right. So in this case, the mode is still the high point. Whatever that score is the mode. The center of the distribution of scores is going to get dragged a little bit by these few high scores. It's not going to be exactly at the mode. It's going to end up being something like this, whatever that is. So the median gets dragged a little bit toward the extreme scores, the ones that there are hardly any of, outliers, you might think of them. And the mean even more so. The mean gets dragged even further by extreme scores. So, so the mean is clearly affected the most by extreme scores. It gets dragged the furthest. And this is this is something you need to remember. What happens to these measures of central tendency when you have a non-symmetrical curve for your frequency graph? Now, I had a teaching fellow when I learned this stuff, and she had ways of teaching us stuff that wasn't entirely mathematical, it was just helpful. So I'm going to do that for you. So notice the alphabetical order of the words, which has nothing to do with math, and I shouldn't be telling you this. But mode, median, mean is reverse alphabetical order. So if you think of this as a mountain, and you think of this as, if you like to ski, as skiing, you're skiing in reverse alphabetical order, going down the slope that you would ski, not the slope that would kill you. And if you like to climb mountains or you're forced to hike up mountains, you would pick the side that was a little more gradual. And in that case, you're going up that side and it's in alphabetical order, mean, median, and mode. In any case, the alphabet's your friend here to remember this. This particular shape, I'm going to make sure I get this right. Don't just wait right there. I've been known to say it backwards and it's ugly when it happens. Yeah, okay. It's positively skewed. So skewness. Skewness is when a frequency curve or frequency distribution, either way you want to think about it, is asymmetrical. There are outliers. Outliers, it's not liars like you lied to me. It's liars like they're lying on the ground. Outliers are extreme scores. Really different from everybody else. It's kind of when you give an exam and the scores range from 10 to 80, and then you have two people who got 98. Outliers. And they do what we call killing the curve. Because if I was going to make, as some teachers do, if I was going to make the mean score a C, in a symmetrical distribution, look at these scores, it would be lower than if there were outliers getting 98s. That drags the mean up, makes it harder for everybody else to pass. See how that works? That's why we don't grade like that, most of us. Most of us pick a range, of a number range. That way, whichever way the curve goes, your grade isn't getting affected by how others do. Because your grade being affected by how others do, to be honest, gets on my nerves. I don't like it. I won't do it. Okay, so skewness. When a frequency curve is asymmetrical, there are outliers. In this case, there are outliers in the positive direction. If this is the score of 0 on the test and this is a score of 100, these few people over here, they're outliers. And we call this positively skewed. It's like it has a tail going off to the right in the positive direction on the number line. Now, I'm sounding like this is the most important thing you've ever heard because inevitably I have students every year who get this wrong on either a quiz or an exam or both. And I can't quite figure out why, because it's easy to memorize. So memorize it. Okay. We also have negatively skewed. This is when you have a few people fail an exam, but everybody else did pretty well. So this looks like this. Same thing, we have frequency, we have score. And it mostly was an easy test. Most of the people did really well, but you have a few people who failed it. This is what the grades in this course tend to look like, by the way. Almost always it's like this. So you have one or two people down here, especially in the first exam, because they actually aren't paying attention because it's also easy to them. And then they get in the exam and they're like, oh shit, I was just riding the wave of the teacher's voice and didn't study. So the first exam scores look almost exactly like this. So this is what we call, well, first let me show you them. It's negatively skewed. Let's just write that out, negatively skewed. I want to show you what happens to the mean, the median, and the mode. I think you're going to be able to guess, but I'm going to tell you anyway. The mode is always the one that has the highest frequency. So this is the mode right here. The median will get dragged toward the extreme score a little. Because don't forget, it's trying to separate the area under the curve, 50% and 50%. So when you have some people drag the curve out all the way to the left, your median's going to get dragged a little bit to the left. So there is the median. This is the mode, the median. And the mean gets dragged even further. And once again, if you're climbing up the hill, in alphabetical order, you go past boulders that say on them mean, median, and mode. The mode's the top of the mountain, yahoo. If you ski back down, you're going in reverse alphabetical order, don't hit the boulders. Okay? How are we doing? Any questions so far? One of the problems with share my screen is it makes you all really small and it's not fun. I don't like it because I can't see expressions. And I don't even know who this is whose ceiling I've been looking at the whole time. Who is that? Is that Shaq? Shaq. Gotta be. Are you there? Yo, Shaq, are you there?
I thought it was on my face.
No, it's okay. I'm just making sure you're awake.
Barely.
Yeah, okay. As long, you don't have, if you like, you can just wait and look at the recording. The problem is that it might be easier to see it and ask questions. So if you wake up and you don't know what's going on, just ask. Good night.
Okay.
Sweet dreams. I'm cutting people lots of breaks because of COVID. I've decided to, anytime you ask, can I have an extension on something? I'll just say yes. So just be nice to everybody. Okay, so those are the shapes. We have the normal shape. We have the skewed shapes. Negatively skewed means you have a few negative scores. They're more negative than others. And positively, you have a few positive. And it changes the shape of the curve. There are other things that change the shape of the curves. Now I'm on a topic called kurtosis. Can't make these words up. That's as neat as I've ever written anything. Kurtosis. Kurtosis is the spread of the curves. How spread out are the scores? We're going to get into how we compute that next after this. But first, I want you to see it in a picture so that you can, and I'm going to refer back to these pictures. We refer to 3 different types of kurtosis. Okay, so this is frequency, score every time. Frequency, score. Normally I wouldn't bother writing this, but since you're going to have it in your notes forever, I figure I might as well. Okay, so let's say that you have the scores spread out reasonably. Just imagine middle-ish spreading out of scores. Looks like what we always think of as a normal curve. But what if instead the scores are squeezed really close together? We have names for these, leave some space. The scores could be really squeezed together. So everybody got, let's say here's the mean, and here's the mean on this one. Let's say everybody got really close to the mean. Instead, it would look like that. And if you had something where here's the mean, and the scores were really, really spread out, it would look more like this. Notice, in this case, I'm talking about symmetrical curves still. They're still normal curves. Normal curve really means a family of curves that are all symmetrical and bell-shaped. But there's lots of bells. A symbol is considered a bell. Look at the bottom one. Looks like the shape of a symbol. I don't know what bell is in the shape of the one on the top left. I have no idea what kind of bell that is. But you can imagine that there's a bell with a little clanging thing inside. Okay.
I have a question. Sorry.
Go ahead.
Because like I think it was last class we saw like how people can like manipulate graph a graph with like scale.
Yes.
Could this theoretically, if like done incorrectly, obviously be just the same graph? Just the scale would have been changed.
Oh, by stretching?
By stretching or condensing.
Yes. You can make it look that way. Remember the curve with the guy's face? And the guy's face behind it?
Yeah, that's what kind of
got more steep or it got flatter. That's the same principle. You're right. So with kurtosis, if you make the y-axis really tall, you're going to make a curve look like this one. And if you flatten it so that the y-axis is really short, you're going to make it look like this one. If it's 3/4, so if you have a curve that at the right dimensions looks like this one here on the top right, then stretching the y-axis will make it look like this one over here, top left, and compressing the y-axis will make it look like the one on the bottom. And both of those ideas are considered wrong, right? So that's how people lie with stats, though. It depends on who your audience is. I mean, if you're showing this stuff to a bunch of stats professors, they're going to say you're cheating. Students who've been through a course like this, they're probably remembering that you're cheating. But most people who sit in a boardroom have no idea what the shape of a graph is supposed to be. So those of us who are honorably doing this as academics all agree. So in the professional journals, academic journals, they're all set to 3/4.
So like in a journal, you'll never see a graph. Like you'd see a graph because the
Hardly
data
ever anymore.
would show that, but it would never look like that.
That's right. Okay, so there's a name for each one of these types of kurtosis. The one that's really tall and narrow is called leptokurtic. I promised you I didn't make up these names for you to have to memorize. The one that looks like more like a normal curve that you've seen before, top right, we call mesokurtic. I'm pretty sure this all comes from Greek. And the one on the bottom is called platykurtic. Now, most people think of a plateau, and then that helps them remember which one's platykurtic and which one's leptokurtic. But that teaching assistant of mine back in 1985 or 4, she taught us to think about Superman for the leptokurtic as if he can leap over tall buildings. Mesokurtic is just for middle, right? Middle. Or it looks like meso for muscle, the guy's like Popeye flexing his bicep. And platykurtic, this is not my fault, and I'm a terrible artist also, but body, legs, eye, platypus. I know it doesn't look like one, but platypuses have really long, have you ever seen a platypus? Should Google it. It's actually, I could do that for you right now, but I won't. A platypus is an animal with a really long, wide beak-like thing. It looks like a combination of a reptile and a duck. It gets its name from the same root for the same reason. Okay, so when we look at these 3 curves, what we're looking at, what makes them different is the average distance of scores from the mean, right? If a lot of scores, the average of scores is really close to the mean, we get top left. If they're a different distance from the mean, we get top right. And if the average scores are really far from the mean, that spreads it out even further to the bottom. So why do we care about the average scores? Well, think about this. Pretend we're talking about exams and you're the teacher. And in all of these, they have the exact same mean. Say the mean is, I don't know, 75. So you're on a break and you're agreed to have lunch in the dining hall. I know we probably never do this again, but you pretend to have lunch in the dining hall. Is the dining hall open? Is our dining hall open? All right, so you have lunch in the dining hall with a colleague and they say, hey, you just gave a test this week. How did your students do? I know you were wondering. And you say, well, the mean was 75. Okay, you could be talking about a group of people who all scored between 70 and 80. Or you could be talking about a bunch of people who failed it and a bunch of people who got 100. If you want to really talk about how your students are doing, you could say, yeah, they were all really close to the mean. It was 75. Or, wow, those scores were really spread out, but the mean was 75, like that. We actually care about how spread out scores are for many reasons, for many variables. So it matters whether they're skewed, it matters whether they're spread out or not. And when we're trying to describe results of our experiments or how a med works on somebody, these become vitally important. And so we calculate them and we put them into numbers that we can then use to do further analyses. Let me show you a little bit about what I mean. Let's say this is score and this is frequency. Let's say that in like an experiment in the old days about how children were on the playground with aggression. So we observe them for an hour and they get an aggressive score. Okay, I'm going to make girls probably another color here. Yeah, I'm going to make girls pink and I'm going to make boys blue because I can. Okay, if all of the girls had low aggression, really low aggression, all of them, that might be what they look like. And then let's say the boys came in and they did like this. When we talk about the difference between groups, we're talking about the difference between means. And it's clear these are two different groups. They don't even overlap. We don't have to do a statistical analysis. They are clearly different groups. This is not what it's really like. What it's really like, even if the means are this far apart, is more like this. Score, frequency. Oh, look what I did. I keep trying to do this, not because I care about it, but because it reminds you that it's a thing. Usually what you get are scores more like this. I'm going to try to keep the means where they are. Pardon me a second while I get right in front of my iPad. To some degree, curves overlap. And this area of overlap here matters. And the overlap is happening for two reasons. One, because the means are where they are. If you make those means closer together, they'll overlap, right? The closer together the means are, the more overlap you'll have between the curves. If these two means over here on the left graph, instead of being where they are, if they were here and here, those two curves would even overlap. In this case, I put the means just where the other means are, here and here. They're about the same distance apart, but they don't necessarily look like they're exactly different groups. You could conceivably picture a curve that goes and covers both of them. Often the groups are that far apart. Sometimes it's more like this. And so one of the things that we're going to be doing are t-tests, and t-tests are always looking for the ratio of the difference between means, how far apart these groups are, relative to how spread out each group is. How far apart the means are matters, but if there's tremendous spread and therefore overlap between them, then maybe you're not looking at group difference. Imagine this as medication. You can't be sure that the high dose is better than the low dose. You have some scores that are higher. Say it's on mood. You have some scores that are higher from that high dose med. That's this one over here on the right. Yeah, you get some people who score really nicely, but you also get some people who aren't doing so well. And even the low dose brings people's scores up pretty high, but also some people are even lower. So is there enough of a difference between low and high dose to be worth the side effects, for example? Well, you have to do an analysis to find out. You have to calculate, and you have to compare it to what would be acceptable, that sort of thing. And that's what we're going to learn how to do eventually in a couple, 3 weeks. You're going to learn how to do an analysis called an independent t-test, which will look at a comparison of how far apart the means are relative to how spread out the curves are. So the spread of the curves is very, very important, especially when we're talking about to describe a group or to look at the difference between groups. Any questions on that? Anybody want to tell me they're lost? Nobody's telling me they're lost. Okay, then. So that means I'm going to move on to this topic of variability, the spread of the curves. Hold on, I got to get my new notes. Here we go. We need to have a measure of this spread, right? We need to talk about it and share the language of it. And the language of it is, we talk about spread, but the more technical language is words like variability, that gets used, range, that gets used, dispersion, deviation, variance. All of those are words that talk about the spread. Let me give them to you again, because some of these you're going to learn, especially we're going to use the words deviation and variability. But also, we know what range is. I'm going to cover that briefly. Sometimes you hear the word dispersion. The word dispersion doesn't show up in formulas. The words that show up in formulas are standard deviation and variance. So I'm going to teach you how to compute, and you're going to love it, the standard deviation and the variance. Also, I'm going to just remind you what the range is, and let me start there. So the range, and that number, that's the range, we don't put into any formulas, we just sometimes write it. And the way that we write range often is low number dash high number. We don't do the subtraction +1, we don't do any of that. So the range is the difference between the high score and the low score. But the way that we're going to write it out is just low number dash high number. So on the 1, 2, 3, 4, 5 example, it's 1 dash 5. That's it. 1 dash 5. That would be how we would write range. Okay, so we need to come up with, in order to describe this deviations or distances from the mean, we need to come up with a numerical way to describe the average distance from the mean. That tells us how spread out the scores are. The average distance from the mean. So let's take these numbers 1, 2, 3, 4, 5. If we're going to get the average distance from the mean, then instead of putting x over n to get the mean, we could put each score minus the mean, that'll give us the deviation, over n. That'll give us the average or the mean distance from the mean. Questions? Please ask if you have a question now, because it's important. Okay. What? Yeah, I'm about to. Okay, good. So I'm going to use 1, 2, 3, 4, 5 because it's so nice to have that in your notes. Okay, so 1, 2, 3, 4, 5, we're going to find the average distance from the mean. I'm going to write it again here, 1, 2, 3, 4, 5, because it's easier to add numbers vertically. Actually, it's the sum of the average deviations over n. Sorry about that. We're going to add up the differences from the mean, and then we're going to divide by 5, n. So does anybody remember the mean of 1, 2, 3, 4, 5? Somebody say it, please. Put me out of my misery. Honestly. It's 3, yes. Okay, 3 is the mean. So to get these, we first have to add them all up. So 1 minus 5 plus 2 minus 5. I'm sorry. That was completely wrong. 1 minus 3. 1 minus 3 plus 2 minus 3 plus 3 minus 3 plus 4 minus 3 plus 5 minus 3. So we go to add those up. 1 minus 3, negative 2. Negative 1, 0. 1, 2. I add them up. What do I get? I need way more participation.
0.
I get 0. That's right. Was that you, Shaq?
Yeah.
Thank you down there. You know that what we see is your ceiling, so I think of you as below. Like in a basement below. But thanks for participating. I appreciate that. So the sum of it is 0. Oops, look what my notes are really. It's so bad. Okay. So the sum is 0. So if I put 0 over 5, because come on. Unbelievable. Hang on. I have to find my unbelievable. Come on now. I've lost my, oh, I see. Now I got it. Okay. If I put 0 over 5, I get 0, right? 0 divided by anything is 0. That tells me that the average deviation of every score from the mean is 0. The numbers were 1, 2, 3, 4, 5. Is the average, what does it feel like the average deviation from every score is 0? The deviation from the mean is 0? It can't be, because that would mean all of them were the number 3. The only way to get 5 zeros here is to have the numbers be 3, 3, 3, 3, 3. There are deviations. You've seen them. 1, -1, -2, +1, +2. The deviate and 0. That number has to be bigger than 0. 0 means they're all the same number. So this is a problematic formula. We can't just use this formula because there are positive numbers away from the mean and negative numbers away from the mean, it zeroes out. So we have to fix that by changing these positive and negative numbers. We need to transform this list somehow so that we don't get that 0. Basically, it means we're going to have to transform those negative numbers. So what are some ways to transform numbers? Does anybody remember liking math in high school and remembering how you transform numbers?
Can you square them?
Wait, say it louder because you're not coming through very well.
Can you square them?
Yeah, you could square them. That's one way to transform numbers, to square them. There's a lot of other things you can do. You can turn them into logarithms. You can get their absolute value. There's a bunch of things you can do. In this case, squaring them is exactly what the mathematicians first grappling with this issue very long time ago came up with. we're going to square them. Okay, let's do that. We're going to square this list of numbers so that we don't get a negative number. So -2 squared is, I'm going to put this all over here, 4 plus 1 plus 0 plus 1 plus 4. That's squaring them, right? And I get 10. So then I take 10 divided by 5, and that gives me 2. Well, that's lovely. Now I have a positive, a number that's real. I have a real number that's positive. Because distance, it may look negative, but the actual distance itself is not a negative number. Right? So you have to do something to make them all so that you can count all the distances. So you get this, but the problem is that since you squared them, all the numbers are too big. They don't really represent the average distance. They represent the average distance squared. So you have to transform it again to match your data. You squared it all to begin with, so now you get your answer 2, and you take the square root of it to get the real answer, which is what? What's the square root of 2? Somebody must have a calculator. Say it again, Sam. Sam, you break up badly today. I couldn't hear a word of that. 1
It's
point.
1. Yeah, 1.41.
Okay. Is that what you said, Sam? Yeah. Yours is terrible today. I don't know what's going on. I suggest you get an Ethernet cable if you don't have one. Honestly, that's what I did. It changed everything. I went from my Wi-Fi to Ethernet. I had to get a doohickey. It's a technical word. Be careful how you throw it around. To connect the Ethernet cable to the laptop. And if you want to connect it to like an iPad, this is a kind of a little doohickey. It's got a lightning at one end, and the other end it'll take Ethernet or USB or another lightning. These work. And then for the for this laptop, I had to go from Ethernet to USB. And some of you actually have an Ethernet port right in your laptops or desk computers. Highly recommended, changed everything in this house. Okay, so this is generally the idea, but what we don't want to have to do every time we do data collection is create the list of numbers, square them all, and then take the whole and square again. And in their wisdom, old times, not psychologists, mathematicians created the formula that is preferred. Also, remember the idea that samples aren't perfect replicas of populations. They're just as representative as we can get them, but they're not perfect. Since they're not perfect, in the denominator, they did a correction. And so instead of dividing by n, for some reason, and this is very unclear in the literature, they thought it would be better to divide by n-1 to correct for samples not being populations, so that we don't overestimate the perfection of a sample. Okay, so here's the formula they came up with, and I tell you right now, it's not pretty. It's not pretty. Nobody's going to like it. You're just going to have to learn it. You do not memorize formulas in this course. You will always have access to formula sheets. Okay, so here's this one. We call this average deviation the standard deviation. Stupid sheet. So frustrating to work with. Every time my palm touches the laptop, the tablet, it shrinks it. Okay, standard deviation. Standard deviation equals, there's a giant square root sign over the entire thing. And a fraction in there. The sum of x squares minus, and there's a fraction here. The sum of x, get that and square it, put it over n, and then put the whole thing over n minus 1. This works better for early computers and for some other additional computations that people were doing that were popular at the time. They needed to get these things anyway, so they just created this formula for standard deviation. It got it done fastest for some reason. It seems like it's a big runaround work. Okay, so there's two problems that students run into typically with this formula, even though I give it to you. One is you forget that there's a giant square root sign over the whole thing. You get your answer, you're all excited, but you forget to take the square root. So remember to take the square root. And the other is the difference between this sum of x squares and this sum of x squares. They're not the same. And this is where you must start to remember order of operations. We do what's in parentheses before we do exponents. Remember that? What's that? What's that? I don't know, because your sound is terrible today, but whatever that bunch of letters is that you had to learn when you were kids, that tells you what to do in what order. Somebody who knows their mic is working.
Like bed mass? Is that what you're saying?
Oh, Isaac can do it. Yeah, what is that? That one, Isaac.
Bed mass. It's like brackets, exponents.
Hold on a second, I'm messing up here and I want to write it down for everybody's notes.
We do PEMDAS.
Oh, sorry, I did the Canadian version, so it's
We do PEMDAS in this space.
because you guys can't spell and make a word.
All right. That was-
I agree. I'm with you on this. Okay.
It was like brackets or parentheses.
So is it parentheses?
In the States is parentheses, yeah.
Parentheses, and then what?
Exponent,
E,
and then division, so D.
D, and then keep going. You're doing great.
Multiplication and addition, subtraction. Or do you guys do M first?
No,
I think we do M first. I remember, I'm old. I'm a lot older than you guys, but I thought mine was, please excuse my dear Aunt Sally. So it was multiplication, division.
Yeah,
that's what we did.
Yeah, so I'm still on the bed mass train, I
okay, I'm going to
Okay.
go with please excuse my dear Aunt Sally because that's appealing. So hang on, I can remember something like please excuse my dear Aunt Sally is wonderful. It's all warm and fuzzy. I like it. Please excuse my dear Aunt Sally. You guys can memorize this, those of you who hate this stuff. And just remember it, those of you who had to go through it. Okay, so that means that when we look at this one that's green, we're looking at exponents and we're looking at addition. That's what that scribbly looking giant E is about. And then when we look at the one that's yellow, we're looking at parentheses, exponents, and addition. But you have to look and see what's in parentheses before you do the other stuff. That's what parentheses means. So even though addition is near the end of the list, you have to do it early because it's in parentheses. I'm spelling this out for people who never learned it in the first place. Okay, so let's take the numbers 1, 2, 3, 4, 5. Sam, once again, I know it's you because of how I can't hear a word you're saying. Ask Isaac to tell us, or go stand over there. Yeah,
So
much better.
how does addition come into play here?
Because in the yellow one, the addition is within a bracket, you do the addition first.
The sum of X.
The sum
Sum
of
of-
Oh,
X.
yeah, sorry. This
Yeah.
sign here
Yeah.
means add up.
Okay,
It
yeah.
means the sum of.
So X would be like X would be like the frequency, or not the frequency, but like
F's
all of
the
our
data.
numbers added together.
F's the data, whatever you collected, the data.
All right, that makes sense.
Right, so when you go and ask people their mood, those are all data.
Okay,
Those are the X's.
got it.
Okay. Okay, so let's find the standard deviation of the sample 1, 2, 3, 4, 5. Isn't it funny that you're in college and you're using 1, 2, 3, 4, 5 and you still have questions? I love it. That's what stats is like. Okay, let's fill it in here. So S equals giant square root sign, big fraction. The sum of the X squares, that's the first thing. So the first thing I have to do is get the X squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. I add all those together, what do I get? Somebody tell me.
$55.
Yes, 55 minus I'm putting in the easy stuff. I only have one thing left. The sum of X squared. We do the sum of X first, it's in parentheses, and then we do the exponent and square it. So what is the sum of X? 1 plus 2 plus 3 plus 4 plus 5. 15.
I have a question.
Yeah, Shaq, what?
Come from, like, for N.
Yeah.
Where'd the 5 come from?
Oh, there's 5 numbers.
Oh,
N is the number of data points. Does that data points work? Is that a good word for you?
yes.
The number of responses, the number of things that you measured, the number of people in a sample.
Gotcha.
And if you have 2 groups, it's the number of people in that one group. Okay, let's keep working this formula. The giant square root of 55 minus, what's 15 squared?
25.
Say it again.
225.
Yep, 225. 225 over 5, all of that goes over 4. Keep working, 55 minus what? What's 225 divided by 5?
45.
45. You like my example? Put that over 4, the square root of 10 over 4. Notice I keep moving the square root sign down with me. It's the only way to remember. If you leave it off, you'll never remember that it's there. All right, what is the square? What is 10 divided by 4?
2.5.
Thank you, 2.5. And what finally is the square root of 2.5? Wait a second, hold on. We did this earlier when we did that average thing. Oh, it's on the same page, isn't it? It's like, remember that thing that we did that's very, oh, it's lost. This. Remember all of that? We got the square root of 2 and it came out to 1.47. Is that what it was? So we already got this answer, 1.47. but you're not going to like this. What's the square root of 2.5?
One point five. 1.5.
And the answer is 1.5. Okay. Standard deviation equals 1.5. So why isn't it 1.47? Anybody remember what I said about samples versus populations a little while ago?
That one,
Yeah,
because
yeah. Because we put n minus 1 in the denominator instead of n, we get 1.5 instead of 1.47. So we're always going to do that, whether we're working with a sample or a population, because I don't want you to have to worry about which formula to use. It's just a dumb thing that we should let computers worry about when they're doing the work. In fact, when they're doing the work, you have to press a button to choose whether you want the denominator to be n minus 1 or just n. So, and sometimes it says sample or population, sometimes it says n minus 1 or n, depends on the software. In this case, for this course, there's no reason to learn both. It's a tiny trivial difference, and all having you do both would just basically be to harass you. So I'm just going to leave it with 1. We're going to pretend we always have samples, n minus 1. Okay, so the standard deviation is 1.5. So now here's what we know about this set of data, 1, 2, 3, 4, 5. We know the range, because we don't have to do anything to know the range. The range is equal to 1-5. We know the mean. The mean was 3. You got that by adding them all up, getting 15, dividing by 5, because that's how many there are. And you get 3. We know n, I should have put that first. There's 5 numbers. N is 5. We know the median. We count in from both sides. Eliminate 5 and 1, eliminate 2 and 4, you're left with 3. 3 is the middle number. They're in order, and it's the physically middle number. So the median is 3. What's the mode? Trick question. What's the mode?
There isn't one.
Thank
There
you.
is
No mode. None. It would look like a flat line on a frequency curve. There'd be one person for 1, one person for 2, 1 for 3. It would just look like a flat line. Okay, and we know the standard deviation, 1.5. There's one more measure that we do to talk about the variability, the dispersion of scores. We get standard deviation, well, range, but we never use it. Standard deviation. And then the other one that's used in formulas sometimes is variance. I'm going to put this here so that we can fill it in so that you have it there. Variance. This is going to be really easy. You're going to like this one. The variance is the exact same formula without the standard deviation. So it's S squared. Conversely, if you get variance first by any chance, the square root of the variance is equal to S. These are just the same thing and said in 2 different ways. The formula for variance, if you want to do it the hard way, but once you have one, you can get the other without starting over, which saves you a lot of time on quizzes, exams, and just general getting it accomplished. Now, when you put all of this into a piece of software, it spits them all out at once. But if you're somewhere where you only got the standard deviation, which is common, and you really needed the variance for, I have no idea what reason, but you might, you just get it by squaring the standard deviation. So what is the square of 1.5? Someone.
2.5.
2.5? Did anybody else get that? What did you
I
get?
got 1.2.
Okay, that's interesting. So
Oh no, shit. Ignore me.
okay, that means I have to ignore Sam because he was nodding. Okay,
You wanted the square of it?
square of the standard deviation. So 1.5 squared.
It's gonna be 2.5.
Is it 2.5? Anybody else? Yes, Shaq said that. All right, we're gonna
Does
go.
it have to be 2.5? Because to get the standard deviation, the last step is to square root it. So it would just be the.
Yeah, it has to be whatever you had before you square rooted it. That's exactly right.
It may be a little off if you do just 1.5 with rounding, but I don't think so.
I know that's why the reason why I like to round to 2 digits. First of all, it's what's accepted generally in journal articles, but also because it gets us a little bit more precise when we do this big change, which is to square to get the variance. That makes a big difference if you don't go out to 2 decimals. Okay, I mean, here's when it makes a difference. When you're asking people on a scale of 1 to 7 something, going answers for standard deviation and variance out to 2 digits makes a difference in formulas. Makes a difference if you're going to find a significant difference between 2 groups or not. It changes things. I guess that's what I meant to say all the time. It changes things. Okay, so that's a whole topic. I spent a whole week on the introduction stuff and then how to describe data, but this other way to describe data, pretty much the last way to describe data, is how spread out scores are. So now what you noted about a group of scores is how to collect them, one way to collect them, how many you have, how to show them in a table, how to show them in a graph, and then now we're going to crunch some numbers. What's one central number we can use instead of handing people a picture when they ask us a question about how a group of scores looks? That would be ridiculous after a while. You start to feel like you're, pre-technology, like you're from the 1400s. How did your group do here? And you show them a graph, a picture of a curve. So you have that though, because people love pictures. And then we have the one central tendency number, because sometimes people just want that one number that we have. So we use that one number, central tendency, and we use mode, median, or mean. We almost always go with mean, but there are some times when median's best. We'll go back in your notes to look at that. And then we also talk about how spread out the scores are, because a class mean of 75 on an exam could mean a bunch of different things. And in some formulas, you need variance instead of standard deviation. So I showed you how to get that. That's your bonus. That's a lot so far. Going from I hate math to this, that's like giant. So good for you. Congratulations. I'm going to put up some practice problems for you to do. And I suggest that you do them before the next class, because we're going to go over standard deviation again. And that way you can come in with specific questions, knowing what you don't know how to do. But if you want to wait and do them after the next class, that's okay, because we're going to do some practice stuff. I'll just give you some data and you'll do that. And then after we're done with standard deviation, probably before the next class is over, we're going to hell. We're going to start working on Z-scores, which is everybody's least favorite part of the course. Once we go through all the stuff with Z-scores, the last topic is just a little bit of probability, very little bit of probability. And then you'll be ready for your first exam. Okay, so first exam will be not next week, but the week after next. I just don't know which day yet. And I'm seriously considering making it asynchronous. So I'm not yet. I haven't given a math exam online yet, so I'm figuring out how best to do it. And if you have opinions about that, feel free to email me or chat, or I can give some class time to it. Actually, that might be best, huh? Then we can bounce ideas off of each other. All right. I'm letting you out early in celebration of the fact that we got this far today. This was excellent. So look over the notes, listen to the lecture again, parts of it if you have to. I know I'm wordy and I apologize, but I have found over the years that it helps sink it in if I just be my natural self and not try to robotically go through math. So